Hello. Hello, please comment yes if you can see me. Hi guys, please comment yes if you can see me so that we can start. Uh, Please let me know when I'm visible. Are you able to see me? Please comment yes. Cool. So okay, let's wait for a couple of minutes and then we can start spin all. But I'm assuming so today we are going to cover our third session of graph series, and I'm assuming that you have seen at least the first session, not even if second. Then because you should know BFS DFS basics to uh, get a good understanding of the session. So yeah, okay. Let's wait for just 1-2 minutes. Let's other comes, and till then, if you have any general doubt, you can ask, or we can cover it later, or maybe now. Let's see. So yeah, just wait. We'll start at 6:1 or 6:2. And today we are going to cover Dijkstra and topological sort, which are very, at least topological sort is very important for interviews. Matlab, generally, people ask in interviews topological sort questions. So, and if you have any doubt in between, you get any doubt, you are not asking anything. Sorry, if you're not getting anything, you can ask in comments on this chat box. I'll try to cover everything. So, and if I'll repeat if you are not getting anything, so it's okay. That's why we have a session of around 1.5 hours. Yeah, I'll start DP series after this most probably, because I think we have covered almost all the topics. Most of the topics that are required in competitive. DP is remaining obviously, and that is one of the most important topic. So we'll start after this. And how much movement? So is it? So we can cover this question at the end, because let's for graph session, one more session will be there. The only DSU is remaining, disjoint set union. That topic is not important for the job interviews, but yeah, the questions comes in if you're giving any coding contest or the online coding contest, it generally occurs. Okay, so I'm sharing my screen. Please let me know if you are able to see my screen. Please just, are you able to see my screen? Please. Okay. So okay, so let's start with today. So we're going to cover Dijkstra and topological. First, we'll see Dijkstra, and just this PPT is only for me. Like, matlab, don't rely on this. I'll just teach everything on notes. This is just for if I don't miss anything. Okay, so we'll start Dijkstra, and like always, I'll start with a question so that it's you can more relate to it. So okay, let's start. I think I was wasting any much time. And I'm using this after a long time. Might have some, might have even forgotten this thing. Okay, so let's start with the extra. So here the question is you have given some cities. I'll please listen the question carefully. So if you are given have some cities, like city name for simplicity, we are using it A B C D. Now let's say this is B. Now this is C. And for simplicity, I'm just assuming like this is a path. Basically, A is connected to B. Basically, you can imagine it is like A is having a road to B, B is having a road to C, and A is having a road to C also. And you can say that this is 10 kilometer, and this is also 10 kilometer, and this is also 10 kilometer. Okay. Now you want to find out the shortest distance. Basically, you want to go from A to basic. So you are at A city. Now you want to go to B and C. So you want to find which is the minimum path. Like to C, you can directly go by 10 kilometer, or you can first go to A to B and B to C, which will be 20 kilometer. So there are many paths from one city to another city, and after that you can think here which is the smallest one. So one way is to find all the paths and then compare, right? So if I ask you this question, how will you solve? Some people who might already be knowing Dijkstra, they will directly write कि we can use Dijkstra to solve this. Okay. But if you look closely, and if you remember my previous sessions, I said one thing here: if the edge weight is constant, guys, don't only like whenever you heard shortest path, don't directly jump into the extra. If in 70% of the cases that question can be solved by BFS, I'll tell you how and when. Okay, how I think we covered in the previous session, but let's say when again. So if edge weight is constant, means if the edges weight, which is like 10 10 10, it's same all over, or it's 1 1 1, in 90% of the cases you will get here edges are same. You will just like see, this is, let's say, A, B, and C. This is 1, this is 1, this is 1. So in these type of questions, you can simply use BFS and you can find the distance from A to C. Okay, let's say you just want to go from one place to another place, so you can directly use BFS because you will definitely reach there in the shortest path. If you remember my previous sessions, you must have seen some questions like I'm standing on a chessboard and there is a knight, right? And he wants to reach from here to here, and the distance is 1 1. Basically, he can move to any cell, like a knight can move in the 8 directions. So in that cases, because the edges are same, edges weight are same, means if I go from this to this, or this to this, or anywhere in the any of the 8 directions, I will always have, I'm always taking one step. And so if edges weight are same, you can use BFS. But if you have not seen the previous session, you can watch that first, you will understand. But now, so when do we need the extra? Okay, so let's now come to our Dijkstra. So Dijkstra is used whenever the edges weight are not constant. Constant means the edges weight are not uniform or they are different. So let's say in this case only, if I make something like this, here this is, I'll make this again. Let's say this is A, this is B, and this is C. And let's say these weights are undirected, and my handwriting is bad, sorry for that. So this is, let's say, 2 kilometer, this is 3 kilometer, and this is 10 kilometer. So people can ask here, from A I want to go to C. Basically this is some city, let's say for Allahabad, and this is some city, C for Calcutta, and this is a Bombay, anything can be there. So you want to go from A to C, right? So now you can either go like directly A to C direct. How much distance will you cover? 10 kilometer, right? And if I'll go to first A to B and B to C, it will be 2 plus 3. First 2 kilometer, 3 kilometer, which is 5 kilometer, right? So this is obviously a better way. Now here the graph is pretty simple because it's only 3 nodes and only 3 edges. So you have to find it, right? So you want to find from a source. Let's say this is a source. Source means where are you standing currently? So there will be only one source, and you want to find the minimum distance to every node. Like from A to B, the minimum distance is 2 kilometer. Like in A to C, the minimum distance is 5 kilometer. 2 plus 3, 5 kilometer. So similarly, let's say there are other nodes. You want to find the minimum distance to all of these nodes. And so this is the problem we have. I'm not talking about a solution. I'm just saying what is the problem. So let's say you are also, if you are giving an interview, people generally ask to this college students, how will you implement Google Maps? And let's say you don't know anything, right? So there also you can say, yeah, I have the same problem, and the solution we will look obviously. But you can use this part to explain to the interviewer here, I can solve using some BFS or Dijkstra. Maybe that is not the correct solution, but that is also not a wrong solution, because you can always tell any solution to him. I mean, maybe this is not the most optimized, but this is also correct solution. Okay. Now let's take a good example so that we can understand easily. Okay, so maybe choose the black color. So I have made one example. I'll just go to again my PPT. Let's refer it. Okay, so again, I saw it is used for shortest distance algorithm. the source should be single. Basically, if you want to find for from only one part, like you are only standing at a single city and you want to go to the multiple places, and like already I said, no when use when there are weight on edges, and I think I forgot to it non-uniform weights. So this is the condition. Again, one last condition is negative edges should not be there. In that cases, you cannot apply the extra. So some of the things are there. You have to remember these things at least. I mean, these are very simple. So now let's see an example, which is a better example, and let me draw on the notes so that we can cover it, guys. We will take some time, but you should understand it clearly. If you are not understanding, you can write in chat box. I'll explain. So and let me just make this graph. So this is A. It is connected to B. Then this is D. Just let's make it. D is connected to B. D is connected to E also, and B is also connected to E. And one last node is C, and this is connected to C. Okay. Now let me write the. So you can also imagine them as cities. Okay, these are 5 cities, and you can imagine this 6 as of kilometer. So this is the trick. Like this can be anything. Like I can say this is the 6 kilometer distance from A to B. I can say that it takes 6 hours from A to, if you want to go from A to B. Anything can be there, but this is just a weight on edge. Okay. Yeah, you can apply for the extra for both directed and undirected. Good question, and yes. So this is currently I'm taking an example of undirected. So this is 2, this is again 1, this is 2, this is 5, and this is 5. Okay, so this is the current scenario we have, and we want to, and now let's take here. So now this is the case, we are standing at A. So this is our source, and we want to find out here what is the minimum distance from A to B, A to D, A to E, A to C. So if I take some random example, from A to D, from A to B, I can choose this. To A to B, I can have 6 distance. I can go to B via D. Here first I'll go to A to D and then D to B. In this case, it will be 1 plus 2. There is another path, A to D, D to E, E to B. So there are multiple paths from going from A to B, but we have to find the minimum path from A to every other node. Okay, so guys, there is in this Dijkstra algorithm there are mathematical proofs also, but for now you can understand the algorithm. And that you will find it very easy to do this also, and it's quite intuitive also. So just listen to the steps carefully. We will go with the code later on. Don't even think about the code as of now. Just first understand the algorithm, because I'm assuming that if you are learning graph theory, means you are good enough to write any code. Okay, so we'll just understand first what the algorithm, and I hope I'll also show the code, but I'm assuming that you can write the code on your own. So let's first learn the algorithm, and we'll don't mug it up, just understand how it works. So initially, let's assume you don't know anything. Okay, so like we don't know anything, right? So I'm just making this thing again. So let's say this is some node A again. So basically I'm again making these nodes. This is D and this is E, right? And I don't know anything. I don't know this A to B distances, because we have to find it out, right? So obviously we don't know. So but what we can assume is let's assume this distance is infinity. Okay, that we can assume, right? Let's say we don't know anything, but for now we think here, okay, I don't know the path, but there can be an infinite distance, because in infinite distance I can definitely reach there. Okay, and I am standing at A. One thing I know for sure is like distance from A to A is 0, because I'm already standing there. I hope it's clear till now. So let's say I don't know about the edges and all. This is the basic assumption I'm doing. Like from in A, my current distance is 0, because source to source distance is always 0, because I'm already standing there. And rest, I don't know anything. Okay, so I'm assuming okay, there is some infinite distance that I can cover, and I will reach there. But now again we'll start and we'll try to find how can we find the minimum distance. So what we will do is, let's assume we have a container. And if you have seen my session, I always use the word container. I don't directly go into data structure. So let's say this is some container. I don't know what it is. for now, but it's just a box for me which is storing something. So what I'm doing is, so this is the process. So what you do is, like in BFS, if you remember, you start from source, right? And you push inside that queue. Now, in that there is a queue. Let's say we have a container, we don't know anything. So what I'm doing is, I'm here also we insert the source because we only know about the source. So the source and its distance from the source. So sorry, not the source. What we'll insert is, we'll insert a node and the distance from the source. So currently we only know A, right? This is A. So what I will do is, I will insert this inside it, 0 comma A. So currently our this container only contains A node, a single node. Okay. Now what will happen in every iteration? You can also relate it to BFS if you guys are knowing. So what we do over there, we just pull out one node every time from the container, right, or in the queue in that case. Here also we will do the same thing, but what we will do is, we will pull out the minimum distance. Like, so in this container, we will, right now we are having only one node, but in future you'll see we can have multiple nodes. So what we have to do is, we have to pull that node whose associated distance is the minimum. Okay. So right now, if I see, there is only one node, right, which is A. So we'll pull that out. So in this case, what I'll do is, I'll just click a cross, means it has been pulled out, right? So we have 0 comma A right now with us. Okay. Now one thing which Dijkstra ensures is that you have to, because there's a mathematical proof behind it. You can also go and over. So what is the thing I'm saying? Whenever something is coming out of this container, I can say that this distance will be always minimum. So that thing you can, for now you can just see, yeah, okay, you can just believe me, and after that either we can see the proof in the next video. But I don't think we require it, but you can also obviously Google, and if you want to, if you are more interested in mathematics, you can obviously go and learn that part, see that part, the proof of correctness. But what I'm assuming, once a node comes out of queue, out of this container, the distance will be always minimum, and I can say this is the final distance, and we can mark it visited. Okay. So this comes right now. So I'll just mark it using some, let's use green color. So this is visited. Okay. Now this A is gone. Okay. So now what we'll do is, if you can want to analyze it with BFS, what we do, we traverse the children, because right now from A we know the children. Okay. Here we don't know the other paths, but we know that A is connected to B and A is connected to D, and these edges we already know because we have already know the graph. So we'll see we can go to, so let's start traversing it. So from A I can go to B in 6 distance, right? So basically from A to A it's 0, and if I'll go, because I have this knowledge, so if I use this 6, I can traverse in the 6 kilometer, right, or 6. Okay. And currently I'm assuming that the infinity is the best answer, right? So I can definitely, I can be sure that, yeah, I have found a better path than infinity, at least for now. And so what we can do is, so these things we have to do, like from, so what, I'll just repeat it again. So first we'll insert this node in the container. From container we have pulled out the minimum distance, this minimum distance, and the node. Okay, now node is A. Now we will traverse its children, and its children currently are D and B. Okay, so for B I'll see here, this 0 plus 6 means from distance A to A is 0, and this A to B edge is 6. So 6 plus 0 is 6, and currently I'm assuming that this infinity means the distance from A to B. So what I will do, I will replace this infinity by 6, because at least I have no, now maybe it is not the best path, but at least it's the better path. And what I'll do, I will just push this B inside the container. So it will be 6 comma B. Now it's a blue color only. Okay, it's very light. Okay, now for D, what will happen? It will be 0 plus distance between A to D. 0 plus 1 is 1. So, and 1 is less than infinity. So I will just cross it, and it will be 1, and I will push 1 comma D. This is in the first iteration for A. Right now, what will happen? So all the children have been covered. Now what will happen is we'll again do the same thing. Now what is the same thing? So we'll pull out the minimum distance node, which is, so there are two nodes as of now, right? One is 6 comma b and one is 1 comma d. Don't think about the code, just think we can just do it as of now. Now 1 comma d will come out, right? Because 1 is lesser than 6. So out of all, whichever is the minimum will come out. So 1 comma d will come out. So means this is and like I said, whenever something is coming out, I can definitely say that this is the minimum answer for D. So I will mark it visited, means it has also been visited. Now I will traverse it children like we did for the A. So we have to keep it going like we do in BFS. It's pretty much similar. The only thing is the condition. So now for D there are how many children? A, B and E. So from D to A, like A is already been visited, so I will not see it because there's no point. Now from D to B, okay, so now look closely. So I know here from A to D I can come in one distance, right? And from D to B I can go in two, because this I have this knowledge, right? So which will be, so this is one. If I, let's say, just draw this edge, so this is till distance D. I already know okay, one is the minimum distance, and I also know that D to B edge is 2. Basically there is a road which can take me from D to B in 2 kilometers. So currently now I know that 1 plus 2 is 3, and till now I have found the best part as 6. So and 3 is less than 6, so I will update it to 3 because I have found a better way, and I'll again push it. You might be thinking that we are pushing a duplicate node. That's fine. So now 3 comma b will be there because a better node, better path we have find. Now we'll also go for D to E. Now for D to E, again 1 plus 1. So from A to D is 1. From D to E, we know this is 1. So again 1 plus 1 is 2, which is less than infinity. So we are comparing the current computed path. So this is infinity, so it will be 2. Now again we'll do the same thing. We'll just, if we are finding a better path, we are just pushing inside the container. So this is 2 comma E, right? Now I think all the children have been covered. So after this, and this have been visited. So again we have to follow the same thing. So what will come out right now? It will be 2 comma E, because 2 is minimum out of all these 3. So 2 is coming out. So it has been also marked. So we have to mark visited when something is coming out from Dijkstra, from this container. So now I will do the same thing. Now we might find a better path. Now we'll traverse for its children. So for E, children are B, D and C. So for D we will not see because D has been already been visited. For B, what will happen is, now till now we have found up from till E we can go in two steps, 2 kilometer, right? This 1 plus 1, if you want to see, you can 1 plus 1 for this 2, and for this E, and from E to B it is again 2, right? So I know ki I can also find a path which can take me in 4 kilometer, but already I have found a better way, so this 4 kilometer is greater than 3 kilometer. So we will discard it and we will not push it inside. If we have found some better way here, it's 2, then only we will push it inside the queue. Now this has been covered. So what will happen? This B comma 3 will not go inside, B comma 4 will not go inside, because we already have a better thing inside it, right? Now we'll see E comma C. So this is 2. Current distance from E is 2 plus 5, because E to C distance is 5. The edge is 5. So now I can say, and I am assumed current for now is infinity, right? So I will update it to 7, and I will push this 7 comma C also inside the container. Okay. And till now we have visited 3 things. Basically for these three things I have found out the minimum distance. Now comes now what will come? 6, 3 and 7. So this 3 comma B will come. So now it will come, and now I can say that this is the I have found the minimum path. So now we can fix it. Okay, yeah, this is the best path we can find. So this will got fixed. So this is 3 comma B. Now again what will happen? This we have to follow the same procedure. So its children are A, D, E and C, all of them. But A, D and E have already been visited, so we will not touch them. For C we will see. So till B the distance is 3, and from B to C is 5. So this is 8, but we have already found a path. Currently, we have found the best path is 7, and 8 is greater than 7. So we will not consider it. Basically, we will not push it inside the queue. So for B, nothing will happen, and this container will be the same as it is. After that, 6 comma B will come. So now we'll also check if it is visited, because we don't want to go through again, right? So we don't want to traverse its children again because it's already been visited earlier. It might be looking a little complicated as of now. We'll see one more example after this. So 6 comma B will come, and we'll see here that this has been already been visited, and so we will just pull it out and nothing will happen, and we'll continue the loop. Now last only 7 comma C is remaining, right? So 7 comma C will come. So we'll mark it as visited. We will check its children, only B and E. They have been already been visited, nothing happens. Now when we'll go inside the queue, we'll see how this queue, not queue, the container is empty. It's completely empty as of now because everything has been pulled out. So at that time we can terminate our, if you remember in BFS also, what we do is whenever a queue is empty, we terminate the algorithm. So here also we'll terminate the algorithm, and at the end whatever distance we have will be the minimum. So from A to A is 0, D is 1, B to 3 is A to B is 3, and from A to E is 2, A to C is 7. So this is the final path that we have, final distance that we have got, and this is like the Dijkstra algorithm. You can again repeat, see the, if you are not obviously clearly understanding it clearly, you can again watch the video after the session ends, and you can, believe me, just make this diagram in a notebook and do what I might be doing some fast because we don't have that much time, but you can do it slowly and you can just repeat these steps and you will understand it. For now, I'll just take a simple, again, one more example to make you understand. So let's take, but we are going to do the same thing again. So now let's take one example, very simple, A to B and C. So like you solve the 3 nodes example, you can also solve the bigger example like we solved earlier. So let's say this is 2, this is 3, and this is 10. And again, the source is A. Okay. So again, we have some container. We still haven't talked about this container. We'll see. So now so again, what we'll do, we will use ABC, or be a little faster. This will be 0 because source to source distance is 0. This is infinity and this is infinity. Okay, because we don't know about them. So first of all, what we'll do is we'll push the source inside the container, which will be A comma 0 comma A, the distance and the node. Now we'll pull the minimum out of it, which is only A. So this will come out, means I'm cancelling, means it is coming out. So I will mark it visited. Okay, it's done. Now we'll traverse its children. So currently these are infinity. Now A to A distance is 0. So if you look closely, some node when come out, let's say this some node is X, whatever distance it's have, it means the distance from A to this point is some, let's say, W. So this, and now I also know this, let's say R. So, and I want to go to Y. So I already know the distance from A to X. There might be multiple nodes in this, but for now, what it is telling me, the value above it is like this is in W, which is the minimum. I can reach from A to X, and from X to Y, this is a single child. So the distance edge weight is R, so I can reach from A to Y in W plus R. This is the simple thing we are following right now. So again, let's come here. So right now, let's assume that we have infinity distance. Now first we'll see for B. So 0, again from A to A is 0, and the edge weight is 2. So 0 plus 2 is less than infinity. So I'll just cross it, and we have find a better way. I'm not, so again, I'm just saying better way, not the best way, because only it will be only finalized when it will come outside the container. So this is 2. Now we'll see the other child. So it will be 0 plus 10, which is 10 less than infinity. So I will replace infinity by 10, and we'll push both of these nodes inside the container. So 2 comma B and 10 comma C. Right now again we'll pull out the minimum, which is 2 comma B. It come outside. Now 2 comma B, again we'll do the same thing. it has two children, A, which is visited, so we will not see it. For C, now, so this 2 is this W, like I was talking about. So I know here from A to B, from basically source to B, I can reach in 2 steps. And I also know here from B to C, I know like is in 3, there's a 3 kilometer road which I can follow, right? So it will, total distance will be 2 plus 3, which is 5. And currently I am assuming that 10 is the best answer. So, and 5 is less than 10. So definitely I can replace it with 5, and I will push 5 comma C. So you must be assuming there are two Cs of now. That is absolutely fine. Whichever will come first will be the final answer. So that's why we are taking the minimum first. If you are assuming why you are taking. So now there are 2C, 5C and 10C. But this will come because this container always gives us the minimum value. So now this will come outside. We will mark it visited, and we will check the both the nodes. So both of them visited, nothing will happen. Then at the end, this 10 comma C will come out, but we'll have a condition because we don't want to increase the time complexity. So one way is you can again check it's children, but there is no benefit because it has been already been its distance is already been finalized. So it will come out, we will see here it's already been visited. No, don't do anything for it. And now the container is empty. So now we can say that these are the final distance, like 0, 2 and 5. So these are the very pretty much standard straightforward questions will come on the Dijkstra, but yeah, obviously tough questions can also come. So now let's talk about the container. So before the container, okay, let's see keyword. Now let's think in terms of the code. So this graph information that you already know, right? Key how to store it. But there's a little complexity over here is earlier you have to, if you remember the adjacency list, you store like vector of int of v of 10, right? Sorry, let me write it clearly. So currently, this is the convention we follow to store a graph. So basically, v of x is storing the children of x, like whatever is 1, 2, 3, or 4. But now we also have to store this edge weight. Okay, so here comes the power of pair. That's why I already obvious. That's why I said ki before learning graph, you must be good in STL, and that's why I taught STL first. So what you can use is vector of pair comma int comma int. Okay, let me write it clearly. So what you can use is vector. If you don't know the pair, then you can watch my STL session for this. V of 10. So I'm just assuming for this, what will happen is, let's say this A is 1, for simplicity, the index is 1. So V of 1 will be storing the pairwise, right? So it will store pair of, and let's say B is 2 for simplicity, C is 3. Okay, I'm just changing the alphabets to digits. So it will store like this. So right now, how can you understand it? Like this vector is storing a pair. Every vector, so this is a 10 vectors, right? This is an array of vectors. Basically, we have 10 vectors, V of 1, V of 2, V of 3. And what are they storing? Earlier, they used to store simply int, that is the children, but now they are storing a pair of int comma int, the children and the edge weight. So it will be like this, 2 comma 2, because with B, the distance is 2, 10 comma 3, this is means C, and this is 10 distance. 2 will be storing 2 comma A or 2 comma 1, and that's up to you whether you want to store the node first or the distance. That is up to you. So that's how you can store this value, right? This graph. Okay. Now the second thing comes is the what if you remember the algorithm, what extra things we need. One is the distance, right? We were storing distance somewhere, and we were keep on updating. So distancing nothing but a single D array, because we are storing the distance for this ABCD, right? So distance is 1, 2, 3, 4, 5. Now we can store the distance, right? And another thing what we are storing is the visited, that you already know in BFS how we store, or you must be obviously knowing it right now how to store a visited array. Now the last thing comes is the container. Okay, So container is nothing. We are storing some values, right? We are storing some pair, because we are not only storing the node. We are storing. We are sending the weight as well, some that distance. So if you remember 3 comma a and 5 comma b and some 6 comma c, let's say, and we are pulling out the minimum. So I'm assuming you must be good in data structure. So which data structure will you choose over here? I think which will be a pretty much straightforward answer. You have to find from a collection of numbers the minimum number, right? So what will you use? It's a priority queue. You can also use an array and run the. That's how you should see data structures, because let's say you don't know the priority queue as of now. So what you do is you will just take an array and pull all the numbers. You will iterate through a loop and find out the minimum. So the complexity of searching will be on, because you are iterating. And now you want to improve. What you can do is, instead of using an array, you can use a priority queue, because you will find the number in O of log n. So use a priority queue, which is obviously a heap, and you have to use a min heap or a min priority queue, because you want to find the minimum number. So, and I think now we can look at the code, which will make you Dijkstra more you will understand more. And obviously, again, I'll say, please, after the session ends, try it yourself, not the code directly. First do the algorithm with the same example. And yeah, heap, like someone commented, exactly, we have to use the heap. So you can directly first with the example, because code so I'll just take 5 minutes more. So what I say is, whenever you're starting competitive coding, who are new, they should first learn the implementation, because they logics are simple in the initial questions, but people don't know how to write the code. So initially you find it fine too difficult. You might be getting some TLEs or whatever, but right now we are learning graph. So I'm assuming all of you must have at least solved 50, say 100 questions online, right? So you must be good with the writing the code. So if you understand the algorithm, code will be easy for you, because you have already solved questions. So that's why I always say, first learn the algorithm, learn how it is working, and then code will be the easier part. You can always, there might be some problem with, like, you don't know don't know, but you might find STL difficult, but it will not stop you. You might take 15-20 minutes extra, but you will definitely able to solve. So first learn the algorithm and then go with the code. So let's see the code. Let me just open. Wait, I just wrote somewhere. Sorry, just a minute. Okay. So let's see the code and we'll look at step by step. I'll just zoom my screen. And the question is same, the nodes, and if you look closely, the edges are also same. This is the same example we are talking about. So there are, I'll also show you. So there are 5 nodes and 7 are the 7 edges, right? 1, 2, 3, 4, 5, 6, 7. So again, this is the same input, 5 nodes, 7 edges. Now it is saying 1 is connected to 4 with 1 edge, and 1 is A and 4 is D for simplicity as of now. So 1 is A. So I'm saying 1 is connected to 4 with edge 1. So this is the input we are having. So first of all, let's look at every line. So first I'm taking the number of nodes and number of edges. Now in number of edges, this will be seen x comma y comma weight. So earlier you used to store, like in BFS, you guys just used to store v of x dot pushback y, right? But here we also have a weight. And people, if you don't know the pair current for now, you can just simply assume it's just a couple, storing a couple of integers. So it's nothing but a simple pair. So you can assume that we are pushing y and its weight. Okay. And as it is undirected graph, I'm also doing the same for y, because x is connected to y and y is connected to x. So we are storing the input is x comma y with weight wt, and I'm just storing in the graph. So this is the graph storing part. Now, what is this line? This is nothing but, if you remember initially what we assumed, that every distance to itself, every distance is infinity. Yeah. So int max is a big number, so I'm just taking it int max. So till now it's pretty much simple. Now we are calling the function Dijkstra, and I'm passing the source node. The source can be anything, so don't assume it's always 1. It depends on the question. So you can get 1 as of now. Let's say because here we took A as the source, so the source is 1. Now let's Now this is the main part. This is the algorithm. It might look little big code, messy code, but it's very simple if you understand it clearly. So first of all, if you remember, we need a priority queue because we had a container, right? So what is the syntax? And who don't know the priority queue syntax, please watch the. That's why I all taught before those STL and all. So this is the priority queue. If you remember, here we store the. Okay, I'll just repeat. This is the basic syntax of priority queue. Priority queue. Yeah. So if you want to have a integer priority queue, you can just simply write this and PQ. Okay. So this one bracket. Okay. So this is a priority queue, and but now we want a priority queue of pair of integer. So just have to replace this over here. So this is a pair of integer. Now by default, this priority queue gives us a max priority queue, but we need a min priority queue. So for that, you just need to add this get a pair, right? Now you must be wondering here, okay, there are two things going inside this priority queue. So on what basis it will sort? On what basis it will return the minimum element? So by default, what happens is whatever is going at the first will be the will be considered as a priority. So whatever is going first, like here, if I'll sending the distance first because I want the priority on distance, right? So I want the minimum distance first. So I will push distance comma node. You can also use a comparator and all, but for simplicity, I always use this. Whatever on whatever value I want to sort, or I want the minimum element, I always store it at the first place. So I'm sending the values like this, distance comma node. So this is the priority queue part. Now you can clearly relate what example will be solved. Initially we made a source to 0, right? Because we only know the distance of source to 0. Like the distance of source to source is 0. So we have initialized that like that. Then we are pushing it inside this priority queue. So now you can clearly see what we are doing. We are inserting the distance and the source. So distance and the node number, which is ABCD, and here in this case is 1, 2, 3. Then this while loop starts, and you can say, so if you remember, the condition is whenever a container is getting empty, we have to come out of this loop. So that's the condition. In BFS also you write q dot empty. Now what I'm doing, what we have to do, right? So what we have to do is, like, we have to push out the minimum element. So this is, I'm just getting it out from P. So just for example, initially this priority queue is having a comma 0. Now, so a comma 0 is there, so it will come out. So this current means the node number, because P dot second. If you guys, that's what I'm saying. Please learn pair. It's very powerful. So this pair is coming. This basically a comma 0 is coming up outside, and we are setting this current to P dot second. So we have to iterate on the current node, right? So this is the condition that we talk at the end. If something is already visited and it's coming outside, then you can ignore it to save the time. So for now you can leave it. But now let's say this is the state of current. Okay, and so whatever is coming out, we are marking it as a visited, right? So we are just doing whatever we saw in the example. So that's why I said the code writing is very easy. You can, if you are, after some time you will definitely see your logic part is the toughest part. Code I can write. So now we have to write now we have to write this node values. So these are the edges. So I'm just traversing on the node. So currently A comes outside, and we have to traverse on the children of A. So children of A are 0 to, and we have stored it inside this vector, right? So this is nothing but we are iterating the children of A. So this is from 0 to this size. So what we are doing is, we are checking if the state is not visited. That is the first condition, and this is the most important condition, the second one, and that I'm just especially pushing it out to see what it is. Now let's focus on this condition. Okay, So this is the exactly same thing that we were doing over here. Here, if distance of current, which is, let's say, this, if you remember by example, like I'll just show 1 minute. Where is my, okay, yeah. So for 1 minute, I'm just showing this example A, and like if you remember, this is a C example, right? So distance of, if this distance of A plus this, as we were considering, right, weight of A comma C is less than distance of C, then only we have to insert it inside the queue, right? So this is the same thing we are doing. You might be thinking, because it's my code, it might take some time for you to understand, but if you'll go step by step and start writing the code on your own, you will find it very easy. So what I'm doing, distance of current plus this is less than the distance. So what I'm doing, I'm first updating the distance. If you remember, we used to cancel this infinity and update the distance, right? Whatever is we are finding. So here we are just updating the distance with this, and we are just pushing it inside the queue. So pushing it inside the queue is very simple. Again, make pair, and we are just pushing inside the queue, and we have to just follow the same procedure again and again. So guys, I'll again say these are not the very simple algorithms. We have moved into, I'll not say the advanced data structure, but they're already a very good data structure. So it's not like you will just see and learn in 5 minutes. So you have to definitely spend some time, and you have to think on your own, and you have to solve this example. This is the, just take this example and solve it in your notebooks, and then only then after that start writing the code. Okay. So after that you will easily find the, if you'll find this distance array, you here you will already be having the minimum distance of all the nodes from A. So I think that is enough for the extra. And on the time complexity, we can, for this I don't want to tell, but it's okay. Let's start. So if you guys remember, so all the graph algorithms are very simple. If you can see, it's pretty much similar to BFS, right? And the complexity of BFS was V plus E. That's because for, so what is happening over here, if you see, every node is going inside the queue, in the priority queue, right? So nodes are basically V over here, and for simplicity we never so edges are E in over here. So for every node, whenever it's come out, we only traverse its children. So one thing you can for now can understand is, if we are, so people generally get confused in V plus E and V cross E, right? So what is this? This is means for every node we are traversing all the edges, but we don't do that. We only traverse its children. We don't traverse all the edges. So this is V plus E. That's why over here. So, and this log factor is very simple, because the log factor is coming because of the priority queue. So for these many steps, your loop is running, and you are, for V nodes you are coming outside, and for every edge, what happens is you have to push inside the priority queue, which, and then the heapify will occur. If you must be knowing the heap algorithm, which takes a log n time, right? So that's why it is V plus E log V plus E. Wait, let me think. V plus E, and you are only pushing the nodes. Okay, so there will be at max V nodes inside the priority queue. So it will be V plus, my bad, it will be V log log V, because in the priority queue you have V nodes, not all the edges you are inserting. And someone is asking, we can't have negative edges in the graph. Yes, in the initially I thought like there should not be any negative edges in the graph, only then it will work fine. So this is the complexity, and that's enough for the extra. And I also found some questions for you. This was the only question I remember I solved. So you can solve this question. This TSH path is very simple. This CHAS is pretty much simple again, little, but you will learn many things from this. So at least solve these two questions. This is one from Lead Code, cheapest slide. So you can solve these questions and it will help you. So well, if you remember, just for 1 minute, initially also I taught about the chess part, right? That, so these, so questions, graph questions can be of two ways always. So either they will directly give you the graph like this, nodes and the edges, and you will store in vector and all. And other types of question will be, you will be given graph in form of matrix, like, or chess or anything. Basically, you don't need to store the graph in vector because you already have the graph in the form of matrix or something. Like, you have a knight, again I'm talking about the knight, and this is a chessboard, and you can go from 8 directions. So you don't need to make a graph out of it because you already know the, if I'm at x comma y, what are its children. So this will be having the 8 children, right? So this C chess question is based on that. So just giving you a hint, but you should solve on your own. And Dijkstra is not that much important for the interviews. People will, I have taken many interviews and also given many interviews. No one have asked me Dijkstra ever. But yeah, like in Google or any company, if you're asking about the how to implement the Google Maps, and you don't know anything about the segments and all other things, so you can definitely go via this approach. And also in the coding contest, the questions can come. So now let's move to the topological. This is a very interesting algorithm and very simple also. People generally find it difficult because they generally do it via DFS also, and DFS involves recursion, and whenever recursion comes, we get scared. So we can also solve it via BFS, which I generally prefer. So, but what is topological? Again, before starting any algorithm, we start with a question, right? So topological order is nothing but just printing a graph in some order that we'll see. So what is that order? We'll understand over here. The algorithm is going to be very simple. If you know BFS, any guy can return the code, any guy can write the code, and you will never forget it. So just first learn what it is. And this is very important. I mean, people, even I ask in interviews these topological questions, and other people have also asked me. So this is very important for interviews. So you should definitely be prepared with it. Okay. So these applications are very much, but I think the most of you are the college students, so you must have not worked with Maven or Gradle, but that is one of the most good application of topological sort. So I have found a simple way to make you understand. So what I can say is, like, let's say you are given some edges, not edges, you are given some relations. Like relation is in graph only, right? Like if I'm telling A, B, it means A is greater than B. Greater means this A's age is, or basically I can write A is older than B. Okay. So let's say I'm giving you some kind of these things here, and I think in childhood also we have to get these kind of questions in our logical reasoning, right? A is greater than B, and let's say A is greater than C, and B is greater than C, right? Now let's say we have some, and again same kind of question is over here. Like I'm saying A is greater than B, A is greater than C, and B is greater than C, and you have to print in an order from older to younger, right? Who is the oldest guy and who is the younger guy? So currently they are very less relations, so you can directly say A is the oldest person, and then B will come, and then C will come. Okay, but it is quite common. It's very simple because as of now, because there are only 3 relations. And let's say there's another example: A is older than B, and B is older than A is older than C, and I only have 2 relations, right? So here, how can I print? I can say here A will be the older, but I cannot compare between B and C. So either I can write C first or C comma B first. Okay, that doesn't matter, but this is the order is fine. So basically topological order is, so if I go via definition ना, मैं कुछ समझ नहीं आता यार, मैं बताता हूँ. Wait, so I just copied it from Geeks for Geeks. This is the actual definition. Topological sorting for directed acyclic graph, we'll discuss about it, is a linear ordering of vertices such that for every directed edge UV, vertex U comes before V in the ordering. It's like, I don't know. So this is the actual definition. It's also very simple, but we generally don't understand these terms, right? So in a simple way, I got this way to make you understand, like we are having a relations of older and younger. And now I can ask you anything, print from younger to older or older to younger. So this is the order, and if we look at by the definition, what it is saying, it is a directed acyclic graph. First of all, see this. So directed acyclic graph is, it's very simple. Directed means the edges should be directed, Acyclic means the cycle should not be there. Like, and it's very simple. If I say A is greater than B, B is greater than C, and C is greater than A. So this is a cycle, and by logical also, we are saying here A is older than B, B is older than C, and C is older than A. Is this possible? No, obviously, right? So that's why topological order, topological sorting is not possible in a cyclic graph, and edges should be directed. Okay, so this is definition very simple. If you see, is a linear ordering of vertices. So we are having a linear finding. We are flattening the graph. Basically, we are providing a linear ordering. Linear ordering is because it is a linear, right? And for every directed edge UV, U should come before V in ordering. And if you'll see, U is coming basically if two nodes U and V are here, so you should obviously come before V. So if in this example I say A is greater than B, this arrow means older than B, B is older than C, and what was the third thing? A is older than C. So they are saying if there are two nodes which are U comma V, this U should come before V. Okay, and that's what is happening. So if I see A to B and A is coming before B, B to C, B is coming before C. There is a node between A to C, so A should come before C. That is also doing happening, and B to C, B should also come before C. So there are two ways to understand it. If you are good enough with the all this definition, that is also fine. It's up to you. And if you don't remember what it is, you can also take an example of this older and younger guys. Okay, so I'll go with that because it's very easy to understand by this. I'll again go with the same example. A is greater than B, B is greater than C, and again C is greater than, no, C was not greater than anyone, and A is greater than C. Okay, now let's make a graph out of it, and this is just an arrow. So again we can make a graph out of it. A is greater, this means arrow means A is greater than B, B is greater than C, and A is greater than C. So this is a very simple graph as of now, and we have to print the topological order. Topological order I have already told you, we have to print in ways older to younger. Okay, now the typical graph problem, people find it difficult somewhat because they have mostly have tried it with DFS also. But let's look a very simple algorithm that you will never forget for sure. So let's start. What we can do is, okay, so if you remember in the basics of graph, which is in the first session, I told you two things. One is the in degree and one is the out degree. In degree means number of edges coming towards it. Basically for B, the number in degree will be 1 because only one edge is coming towards it. For C, in degree will be 2. For A, in degree will be 0 because no edge is coming towards it. Okay. So when you want to print from older to younger, it's very simple, right? So this arrow means one guy is greater than B. It means two guys are at least two guys are greater than C. Okay. And 0 means no guy is the greater than this guy. So whatever we have graph, we have to find some source, and we have found our source. So this is our source as of now. So this A we can start with, we'll pick it up and we'll start the things from here. And what we'll do, this is again a simple algorithm. We'll again have a container. So what we are doing is, we know here whose in degree is 0 are the oldest guys. There can be some case also like this. Let's make it graph. Okay, so now this will become 3, this will become 0. Now what will be the answer? It can be either AD and BC, and it can also be DA BC, because D and A are the older guy. We cannot compare between them, right? So we can print them in any order. That's why topological orders can be multiple, but this is not the correct one. Like if I write B, D, A, C, because B is younger than both these guys, so we have to maintain that order. But if we cannot compare between any two nodes or three nodes, you have to leave it. You can print any order. So let's take this example. So what I will do is, initially what we'll do, we'll find out the in degree, which is very simple. We'll see with the code key how can we find the in degree for every node, and we will push it inside the queue. Let's take it queue because you are smart enough now. So this is a queue. I'm just pushing inside it. Basically A and D, and there is some array or where you are storing the in degrees, right? So I'm just writing for now A, B, C, D. So its in degree is 0, B is 1, C is 3, and D is 0, right? So these have already been over there. Now, first of all, again it's a queue, so first in, first out. A will come outside, and what it will do is, and if you think logically, it's very simple to understand. So what I'm doing is, I already know here A I have pulled out and A was elder, right? So what I will do is, I will decrease the in degree of its children, because now let's say because he's already been out, so we can say now we have to find the other members, right? So what it will do, it will just decrease the in degree of its children. So its children are B, so I will decrease it to 0. Basically 1 minus 1 is 0, and for C it will be 3 minus 1 2. Okay, now whenever some in degree becomes 0, you have to again push it inside the queue. So B will come out inside. Okay, now D will come. Now D will do the same thing for its children. So D children is only C, so it will decrease C to 1. Okay, and that will maintain in this array. So currently nothing, no has been 0, so we will not push it anything inside the queue. Now B will come. These guys are already come. So B is come. So we are already printing. A has printed. D is printed. Now B will come, and B will decrease the in degree of its children. So its children is only C, and now C degree will decrement it by 1, so it will be 0, and we'll push it inside the queue. So now C is over there, and C will come, and nothing is remaining because it does not have any children. And this is a topological order. And see, we learned the topological order, I guess, in 10 minutes. So that's simple how it is, but what we to generally in Geeksworks or other sites I was seeing, so they generally explain it by DFS, but I prefer this way. It's very simple. So this is a very simple algorithm, then you can follow. I'll now just twist the question. Question is again same, just with a little bit twist. Come on, let me delete this. Okay, now let's say we want to print, the question is the edges and weights are same. Again, A is connected to B, B is connected to C, A is connected to C, and D is connected to C. Again, now the question has little bit changed. We have to print the from younger to older, right? Now who will be the youngest? Whose out degree is 0? Okay, so you don't need to mug it up here. I have to store in degree or out degree. Don't mug it up. Just go by the question. If I'm asking you, print from younger to older, so you will say here, okay, now I have to start from C, so it's out, because the younger guy will be having the out degree as 0. Okay, so I will now store the out degree. So C's out degree is 0, B's out degree is 1, A out degree, you know, right? The number of edges going from it. Who's, if this is the head, I don't remember the exact words. I think this we call tail. So whose tail are going outside, basically these are the out degree, the number of edges going away from it. So from A, the number of edges going away will be 2, from D it will be 1, right? So this is the out degree. Now we'll do the same thing, but now we will decrease the out degree. So we'll start from C, we will push C comma C over here. Now C will come, it will decrease the out degree of its parent. Now the things have changed. So earlier we were decreasing the children's in degree, now we are just decreasing the parents out degree. So C's parent are D, A, and B. So this will go outside 0, this will become 0, and this will become 1. Now again B will go inside because it says out degree has become 0. Now D will go inside, and A will not go because it still has 1, right? Now B will come, and it will further decrease the out degree of A, so it will be 0. Now A will go out inside. Now D will come, nothing is remaining because it does not have any parent. Now A will come, A also does not have a parent, and we have printed the solution, right? Now storing the parents information, that is pretty much obvious. If you are getting an edge x comma y, you can store a array of parent here. P of y is x. Basically, y's parent is x. Storing the children information you already know, and this q you already know. The code will be very simple. In degree, it's very simple. If you are getting x comma y, in degree of here, let's say id, in degrees of y plus plus, because we are, and if out degree, it will be out degree of x plus plus. So now the question is very simple, and just look at the code. Okay, no pun. Wait. And this is that code. The code is for that case, the older to younger. So nothing I'm doing over here. What I'm doing is just taking the input n and m edges, x comma y. So what I'm doing is storing the graph, because I just need the children's information here, and increase the in degree, right? In degree of y plus plus. Now calling the topological, and if you see, if this code must be looking familiar like BFS only, right? So what I'm doing, like I told you, whose in degree is 0, that will be our source, and I'm pushing inside them inside the queue. Now, while queue is empty, again the same condition, we are fetching from the queue, we are printing it, then popping it, and then traversing its children. We are just decreasing the in degree, and if in degree is becoming 0, we are pushing it inside the queue, and in this way you will get your answer over here. Now these are the standard questions. This is a very simple question, but you might get have some twist over here. Like I'll tell you, people generally ask one question in interviews. So because we generally learn by questions only, so let's look at the question. So let's say you have an array tree. Basically, it's having an array tree, like it's having n children, and it can have up to n children. So the question generally people ask is like, this is a tree. Let's say it's have one more children. So in every operation, in every single step, what will happen is all the leaf nodes will be burnt. Okay. So now let's say in a single operation, these leaves will be plugged or burnt. Then in the second step, so all the leaf nodes basically, right? After this, the tree will be like this, right? Only this thing. Now in the second operation, these tree will be burnt, and at the end, the last node will remaining, it will be burnt. Okay. So you have to perform this operation. You have to write the code for this in a very optimized way, the best possible way. So one way is I will find a leaf node first. Okay, using BFS, I'll go over here, I will remove it. And something people also think, yeah, we will just remove the level, but this is not the case. The tree can be like this also, right? So in the first operation, this, and this we have to remove. So one way is you will start BFS and you will find one leaf node, you will remove it. Then you'll find another, you will remove it. And it will be very slow, obviously, right? But now if you look closely, it is a standard question. It's a topological order, right? Because you have to print the, you have to remove the nodes whose out degree, if I assume it like this, you can obviously assume out degree is 0. So what I will do, I will just first push these nodes inside the queue, and its out degree is 1, 1, 1. So these will be removed, and at the same time, their parent degree will, I will just decrement it by 1. They will become 0, 0, 0. In the second step, these will be removed. Okay. And now I can ask how many operations will it take to remove all the nodes. So in this case, 2 are the answers. So questions can be little tricky, twisty, or anything they can do. But if like recently, Google asked a question to one of my friend. The question is like that. It was like that. A is left to B, and another relation A is left to C, and C is left to D. I can also write E is right to F, and you have to print the order from left to right. Okay, and if you analyze it, it is the same as younger to older, right? This left I can write as A is older than B or younger, and if E is right to F, I can write as I can convert it, right? That F is left to E. And after that, it's a pretty much straightforward topological question. So these are some questions. One question is, I'm not sure who will most of you understand or not, but if you guys have worked in if you are already working in companies, so you must have used Maven, Gradle, or any dependency tool, like which resolves the dependencies. College students might not get it, but if I say I can and I'll try to make you understand. So let's say this is some service A. Okay, service I should say, or let's say package. If you we have some Java packages, right? So let's say this A is dependent on B, right? And A is dependent on C. A is also dependent on D. This D is dependent on E and F, and this is dependent on, let's say, J. Okay. Now the question is how I have to resolve it, right? Basically, to get the package C, I first should have to fetch the package J, right? To get the package B, I don't need anything, so I have to fetch the information as fast as possible. So what I will do is I will, and let's say these packages are all inside a repository or inside a for you can understand, like inside a container again. A B C D E F G E F G. Okay. So now this. So what I can do is I can, in a single iteration, I can just find B, D, E, F, because their out degree is 0, right? Not D, B, E, F, and J. So I can directly fetch them in one go. And now their parent degree will become, like for A, the out degree will become 2 because it was 3 earlier. And for D, it will become 0 because it has 2 earlier, but now both have decreased it. For C, it will become 0. Now I can fetch D and C from it in a single step. But I cannot fetch A because its out degree is still 2. So first I have to fetch D and C. So D and C will come and they will decrement it by 2 because one for D and one for 0. Now I can fetch A. So Maven, Gradle, or any dependency, and you must be using whatever. So they generally use this. They generally use this thing, and you can resolve the dependencies like this. So these are standard application. People also ask this in interviews to people who are experienced how Gradle will work. So this is again and people generally say that competitive programming does not occur in real world. Sometimes people just say so. This is one of the example, like we use topological sort over here, and now I think that's enough for today, and I'll just share the questions. The complexity is V plus E. This is a homework for you. You have to find out how it is V plus E. If you are smart, you can just watch the BFS session, and there the algorithm is almost same in the terms of time. So you can understand how it is V plus E. There are some questions you can see. And this leaf nodes plug problem, I already told you. I was not able to find it on net, so I was not able to paste the link over here. And I think that's enough for today. We have 5 minutes, 5 minutes. You can ask your questions if you are having anyone. And just yeah, you can ask any question if you are having anyone. Any general question not regarding to this session. If you have any question, you can ask. And if you don't have any question, we can quit. Someone asked here, this question is minimum spanning tree important? Earlier someone asked. So again, I will say it was important for the coding contest. In interviews, people generally don't ask it. And disjoint set union is the application of this only. Sorry, minimum spanning tree is the application of disjoint set union, and I will cover that in the next session. So it's fine for, you can obviously come back and learn the session. And someone is asking, saying, okay, someone is asking, can you please introduce yourself? Okay, here I'm Shikhar. I'm just working as a software developer at Flipkart as of now, and CodeBuddy is nothing but it is a platform we made in our college time to help the student. So it is just continuing by that, and that's why I just named the channel as CodeBuddy. Nothing fancy about it. And how Chinese remainder theorem is important? Good question. Chinese remainder theorem is not important for the interviews, again I'll say. But if you are a ICPC aspirant and you want to go over there, and if you're very good in you want to uh, cover more and more advanced topics in the number theory and in the competitive programming, then you can definitely show. Because I consider this important, because in one of my ICPC regional side we faced this question, and at the time we did not know how to solve it, but we solved it. Okay. When are you planning for the system design live session? Okay, so you must be knowing. Okay, thanks. This is a good question again. So I'm not getting enough time these days actually. That's why this session took so much long. So another friend of mine who's a software developer at Grab Singapore and is far more experienced than me. He's a 5-year experienced guy, because system design is something like you can always learn from experience. So I've asked him. He's making those videos. But yeah, those who are, so once one video is already out, you can see that Instagram live mock interview. So people who don't know how a real system design interview looks like, you can obviously watch that. But yeah, we are also making an analysis video of that, because we cannot cover everything in 30 minutes. And people these days also don't want to watch 40 minutes video. I don't know why. But yeah, we are covering that. I think any last question if anyone want to ask. I think we can call it for a day. Is there any website of your channel? No, not as of now. We had one in our college. We used to teach our juniors on that site only, but it's closed as of now. We are again working on it. We might start soon, or not sure. No plan as of now, but yeah, we are working on it for sure. Start DP. Yeah, so one more session on graph, that disjoint set union. After that, the plan is to start DP, and DP is obviously again very important topic. So you have to. I'll also have to invest some time so that I can teach better. Okay, sure. Cool. I think that's fine for today. Where to system? Okay, this is the question I will answer. Where to study system design properly? I'll just paste one channel if you want. This is the who are experienced guys and want to learn system design. I'm obviously uploading them on my channel, but I'm also pasting over here. Please follow this. I'm already pasted inside the chat. HLD you can start learning from here. It has covered almost everything, and after that you can start watching the videos for interviews. But to cover HLD and all the topics in detail, you can definitely refer this. Okay. I think that's enough for today, and see you next weekend. Hopefully, if I'll be free, I'll definitely conduct a session next week. Okay, enjoy your Sunday, whatever is remaining. Bye.